In recent episodes, I taught you a magic trick. The trick was to learn how a set of individuals would respond to interventions, and the magic was that one could do so without actually intervening. The most popular way of doing this is with the backdoor criterion. Using knowledge of the factors that lead observed individuals to voluntarily take the treatment, you can calculate how they would respond to interventions that make them take the treatment. Today I'll teach you an even cooler magic trick. It will allow you to identify an effect without measuring background factors, but by observing the mechanism linking cause to effect. This is known as the front door criterion, and seeing why it works will deepen your understanding of how causes relate to probabilities. Hello, and welcome to Causal Foundations. My name is Naftali Weinberger, and in this series, I introduce foundational concepts from causal inference in videos of approximately 10 minutes. Suppose you're curious whether joining an expensive gym will help you reach your goal of bench pressing 200 pounds. You can't just look at whether people who join come to bench this amount. For one thing, people with different body types will differ in their capacities to build muscle. Moreover, people with more capacity also have more incentive to join the gym. So just observing people who joined and can now bench 200 won't tell you that they can do so as a result of joining. To review, the effect of x on y is given by the probability of y given do x, which is the distribution resulting from interventions on x. This is the quantity we're aiming to identify. Suppose that there are just two body types, A and B, and that people with type A are more able to build muscle mass. If we can measure body type, we could use the backdoor criterion to measure the causal effect. This would be an average of the probabilities of benching 200, given that one joins the gym for each body type, weighted by the percentage of people with each body type. Now suppose that you didn't measure body type, but know that the effect of joining on the outcome is entirely mediated by the time spent at the gym. Under specifiable conditions, one can identify the same effect using the front door criterion. Conceptually, this criterion combines two applications of the backdoor criterion, which identifies the effect of x on z and of z on y. But for the moment, I actually want you to be slightly puzzled about how this effect is identified at all. We already know that the effect in the population is a weighted average over body types. But here we don't actually measure body type. So how is it possible to identify the effect? Unless you're already an expert, this will not be transparent just from looking at the front door formula. But by the end of this episode, it will be crystal clear. The front door criterion, like all identification criteria, relies on assumptions about which variables are deseparated along certain paths. This is explained in episode 2, but the rough idea is that x and y are deseparated along a path if there's either a common cause or chain that one does condition on, or a common effect that one does not. Variables that deseparate a path block the transmission of probabilistic dependence along that path. In order to apply the front door criterion, you need a variable set z that meets three conditions. First, z must completely mediate the xy relationship. So there can't be an influence of joining the gym on the outcome, except through the number of hours spent there. Second, there can be no backdoor path between x and z, such as a common cause of x and z that one does not condition on. Finally, x needs to block all backdoor paths between z and y. Since the only backdoor path here goes through x, this condition obtains. Before going on, I'd like to offer one final clarification regarding the backdoor criterion. So far I've focused on cases like this one, where gender is a common cause of the drug and recovery. Here it's really easy to see why conditioning on gender eliminates confounding. Since gender accounts for the differences in the recovery rate, conditioning on it ensures that you're comparing like with like. But this simplicity makes it harder to grasp why backdoor adjustment works more generally. The graph on the right posits that women and men go to doctors with different proclivities for prescribing the drug. Here z is just as good a backdoor variable as gender was in the first case. But it's still true that you've only identified the average effect of x on y if you get a weighted average over men and women. So how do we get this by adjusting for the doctor variable? The answer comes from a general principle linking interventional and observational probabilities. In a causal graph, the direct causes of a variable are called its parents. Although not all causes of a variable are included in a graph, we're here assuming that all common causes of variables in the graph are either included or indicated by a bidirected dashed arrow. Pearl proves the following condition. It states that the probability of y given an intervention setting x to x is a sum of the observational probabilities of y given x and its parents, weighted by the probabilities of its parents. It reflects that once you condition on x's parents, any remaining probabilistic dependence between x and y is due to the causal relationship. But this is not the only thing going on here. It also matters that when considering the probability of y given x for the particular value of x, one reweights this probability based on the probabilities of x's parents. If one did not do so, unobserved variables such as gender would not have the distribution they have in the population, but rather the distribution conditional on x. Reweighting by x's parents ensures that all such variables have their unconditional distribution, which is the necessary one for identifying the effect. Now for the front door criterion. In the gym example, we'll treat all variables as binary, with x being joining or not, z being above or below 5 hours a week, and y being whether one can or cannot bench above 200. The effect of x on z is trivial. The only backdoor path is blocked by y, so the effect of x on z is identified by the observational probability of z given x. The effect of z on y is more complicated, but it has the same structure as the second model from the last slide. We get the effect of z on y by reweighting it based on its parents x. The probability of y given z equals 0, for example, is the sum over the probabilities of y given z equals 0 for both x equals 0 and x equals 1, each weighted by their probabilities. So we can derive the probability of benching 200 for both spending less and more time at the gym. Once you have these values, you calculate the effect of x on y by reweighting the number of hours by their probabilities given particular interventions on x. Let's bring this all together. Suppose we want to learn how much joining the gym increases the probability of lifting 200 compared to not joining. Start with the probability of lifting 200 given not joining. This is the sum of the probabilities of z being 0 or 1 given x's intervention value, each multiplied by an expression that sums over x. The probability of z equals 0 given x equals 0 is multiplied by the probability that y equals 1 given x and z equals 0, weighted by the probabilities of x being 0 or 1. The probability of z equals 1 given x equals 0 is multiplied by the probability that y equals 1 given x and z equals 1, similarly weighted by the probabilities of x. This whole expression yields the probability of y given do x equals 0. The probability of y given x equals 1 is derived similarly. Note that the part of the calculation within the brackets is the same as before. This reflects that once we take into account the effect of z on y, the only way to change the whole causal relationship is by adjusting the probability of z given x. This is intuitively the right result, but it only emerges out of the thicket of conditional probabilities once you use causal knowledge to arrange them just right. The upshot of the earlier discussion of the backdoor criterion was that x's role in the brackets is not just a matter of blocking z's backdoor path, but also of making sure that the distribution of unmeasured causes of y along this path is the correct one. Today I explained how to use a perfect mediator to identify an effect, even without knowing the common causes that confound the relationship. It's easy to miss how remarkable it is that we can learn an effect that depends on background factors without knowing what those are. It's equally remarkable that whenever it's possible to identify an effect using the backdoor criterion, you get the same effect that you would get were you to identify it based on a full set of mediating variables, even though we almost never have such a set. The front door criterion validates the intuition that learning the mechanism by which a cause brings about its effect is valuable for causal inference. At the same time, it puts pressure on philosophical positions that view causal and mechanistic explanations as somehow competing. Causal knowledge is mechanistic knowledge, in a sense we can make very precise. Thank you for listening. If you're interested in reading about a real-world application of the front door criterion, check out the citation on the screen.